All right, so hopefully you've watched the videos, the last few videos, particularly when we talk about what net work is. Now, it comes from having a net force. If there's a net force, it will produce net work. That the work done by the various forces, another way to look at that is when we add up all the works done by the various forces, some might be positive, some might be negative, but there'll be something left over. There'll be some amount of work left over. So, the other video was just a little bit ago, you might have watched, you may have watched 3 days ago, but you get the idea, was on the changing, what it means to have kinetic energy changing. Well, think about this. There's a connection between these two. In order to change a kinetic energy, the velocity has to change. When the velocity changes, it's got to be an acceleration. So there's a chain of thought I want you to be able to go through here. So, in other words, you can memorize the formula that I'm going to put on the board in a minute. There's a board over there. We're going to write down a formula. It's going to be great. Formula. Great. But the chain of thought will help you create the idea of the formula. The formula is just shorthand for, hey, there's this really complicated, cool idea that we can write really simply with just a few symbols. But if you're only, it's like reading the Cliff's Notes of some novel. You can read the Cliff's Notes of Frankenstein, and you can get, the idea, monster, killed, crazy dude, whatever. Yeah, you can get the idea. You can tell I read it. But you don't really understand what the author was talking about. And I should be able to name the author right now. It's not coming to me, but it's late. I know it. It was Shelley. Was she married? Mary Shelley? Was it Mary Shelley? I think it was Mary. I can look it up, but why would I? So, I digress. Point being is that when we look at the equation, and that's not what's important. This following chain of thought, to me, is more important. So something has its kinetic energy changed. Maybe it's moving and it's brought to a stop. Changing kinetic energy. Its velocity changed. Wait a second. That means if velocity changes, the very definition of changing velocity, the change in velocity, is acceleration. And what I know from doing forces, which is why, by the way, all the tests for this course are cumulative because it all matters, is that changing velocity means there's an acceleration. And if there's an acceleration, that is produced by net force equals ma. That's produced by a net force. So the only way a kinetic energy can change is if there is a net force. Otherwise, Newton's first law, right? Object in motion wants to stay in motion. If there's no friction here, this thing just goes on forever. And so, therefore, there would be no net force in that case. If there's Newton's first law says if it's moving, it's going to keep moving. The only way you're going to change its kinetic energy is if there's some kind of a net force. Then, last step in this thought process. If there's a net force, then there has to be a net work done on it. There's got to be an amount of leftover work. All the different works that are being done by friction, by somebody pushing it, by whatever, they can't just add up to zero. There's got to be something left over. There's a net force. And that net force times whatever displacement is the net work done on that thing. Well, there it is. That entire idea took me forever to talk about, including talking about Frankenstein, blah, 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 all that. It's an important idea. I'm going to write a little formula on the board, but if you really want to understand physics, you want to be able to almost recreate. This formula should be something that you never have to memorize because you already understand the big idea. So, what did I just say? I said that if you know that an object's kinetic energy changes, and then comes all the stuff off to the side, what does that mean for the object? That's great. It's simple. It's change in kinetic energy. Well, that means that, let's say, there's a change in velocity, which means acceleration, which is a net force. Got it? Okay, there's a net force, then there must be a net work done on that. So a change in kinetic energy means there is net work done on it. And in fact, that amount of work that is, quote, left over after you add up all the different, forces and multiply it times the displacement, that amount of work has to show up, conservation of energy, somewhere. And it's going to show up in the fact that the object's kinetic energy is changed. And so, changing kinetic energy is equal to the net work done on an object. And I mean, it's elegant, it's simple, but there's a lot more physics to that than just the silly little symbols written down there. I don't even think the work-energy theorem makes it to your equation sheet in AP Physics, because it's such an important idea to know that it's almost belittling the idea by just memorizing that equation. But man, can this equation get you out of a lot of problems? Because if a problem's talking about the distance something takes to stop, for example, if you start going kinematics before you look at this, you just want pain and suffering, as far as I'm concerned. Because this will get you out and get distance stopped a lot faster than going to kinematics and trying to figure out what the acceleration. You don't even need to know, look at this, you don't even need to know the acceleration or the net force in order to figure out the net work here. Because, well, I guess you could find the net force on it. Maybe you couldn't. But that work done is the net force times the distance. And the change in kinetic energy, of course, understanding what that means is that's the final kinetic energy minus the initial kinetic energy. So not only is, again, this is a nice simple way of looking at it, but you should be able to expand it to its parts. You should know what net work means. It means the net force times the displacement. You should know what it means to have something change. It is the final minus the initial. These are things that we've talked about at this point in the course, and I'd expect you to know. I should not have to point and come up to you. If I have to, don't get me wrong, it's fine, ask. But you increasingly don't want to have to be like, what does that mean? Well, I don't have to come and say, hey, think about it. What does it mean to change it? And write this. This, if you're solving a problem, this right here should just flow from this idea. That's what change in means. It's like if I ask you to put on your shoes and you ask, what do I do with these stringy things on them? You lace up your shoes. Like, that's part of putting on your shoes. And I shouldn't have to explain that to you. Like, put them on. Oh, by the way, those ropey thingies, tie them. Like, no. For those of you who wear shoes without laces, you get the idea. So, this idea is going to get you out of a lot of problems. And we'll see that as we go through and we do some sample problems. Ask yourself, right now, this is an important one. You want to summarize. If you can understand the thought process here, then you can get a lot of what we've talked about for the last bunch of videos. That's in your head. If you can explain that. I'll give you an analogy here real quick. So if my kids are little and they're learning how to ride a bike, so they're coming at me, they have a certain amount of kinetic energy. As my son rides past me, I push the back of the bicycle seat, all right? And if I push in the direction that he's moving, right, I do a force times the net force times the distance, all right? Assuming he's moving at constant velocity when I start. When I start pushing, he has a net force, and he will accelerate while I'm pushing. That force times the distance that I apply it, right, will show up in the increase in his kinetic energy. He was going slower here. He had a certain kinetic energy. If we knew his mass, we knew the velocity, we could figure it out. When I'm done doing that force times the distance, he's got a new kinetic energy. That force times distance is equal to that change. If I took what he had before, what he has now, minus what he had before, whatever that increase is, would be force times distance. Notice I did positive work there, right? He was moving this way, I pushed that way, positive work. Let's look at a slightly different scenario. He's coming past me on his bike, and I think he's going too fast and he's going to hurt himself. So as he goes by, I grab a hold of the back of the seat, and I pull this way while he's going past me. So my force is this way, but he continues to move that way. Now, what have I done to him? Well, I've slowed him down, right? That's the way I would slow him down. Probably break a finger, but that doesn't matter. I slow him down. It's worth it. He's my son. So he had a certain amount of kinetic energy here. Here he has less. That's a negative change in kinetic energy. So the net work done better be negative. Is it? My force was this way, but the displacement was that way. That's negative work. See, it should work out. No pun intended with the work thing, you know what I mean. But these are two scenarios. Object driving along, slams on the brakes, comes to a stop. That's a negative change in kinetic energy. Right? Had some, and then it doesn't. And it's negative work, because the brakes would have done a force in one direction, while the displacement was continuing in that direction. Whereas if you're at a red light, and you start from rest, and you hit the gas, and later you're going faster, you've done a positive change in kinetic energy, and your force and your displacement are the same direction. Right? You can use this, you can imagine, to solve lots and lots of problems, and it will come up quite a bit.